what I'm going to be talking about. First, I'm going to give you an introduction and historical perspective, then going to talk about the objectives, original construction details, the early age performance of the sections, our continuous monitoring efforts, and some final conclusions. So the Illinois pavement design was originally based in the Asher Road test. The Asher Road test took place in the mid-60s in Ottawa, Illinois, and it yielded an empirical design procedure. Now, by the early 1980s, IDOT wanted to update the empirical design tables, but it was apparent that the tables couldn't be updated and take into consideration all the different types of materials and new materials and new construction practices. So by the mid-1980s, the University of Illinois developed a mechanistically based design procedure, and IDOT decided to build 4 demonstration sections to validate this design procedure. And to this time, these sections have provided us really good information. So we had to come up with some objectives. We came up with 4 main objectives. Our first objective of this project was to validate the mechanistically based design for asphalt pavements. We wanted to validate the predicted deflection and strain values in PCC sections. We wanted to evaluate the effect of asphalt binder type. And we wanted to evaluate the effect of joint spacing and configuration in concrete pavements. So we came up with 4 different projects located as pictured in the figure. 2 in the northern part of the state, 2 in the central south of the state. These 4 projects were divided in 53 different sections. We had 10 different pavement thicknesses, and we had 4 different pavement types. And each one of this project is linked to one of our objectives. So project 1 was located in the northeast of the state on just close to Freeport, Illinois on US 20. It was 3.8 miles of 13-inch full depth HMA. This project was divided in 2 sections. Section A was built using AC10, which is similar to PD58-22, and Section B was built using AC20, which is similar to PD64-22. The main objective of this project was to evaluate the influence of asphalt binder in pavement performance. Project 2 was adjacent to Project 1. It was also on US 20, just northeast of Freeport. It was 2.8 miles of 10-inch PCC over 4 inches of Cam 2 subbase. Cam 2 is a subbase is a cement aggregate mixture that contains a minimum of 200 pounds of cement per cubic yard of material. So basically, it's a stabilized subbase. This project was divided in 9 sections. We had 2 20-foot jointed plain concrete pavement sections, 2 40-foot jointed reinforced concrete pavement sections, 2 15-foot jointed plain concrete pavement sections, and we had 3 different hinge joint designs. Our 3 hinge joint designs, we had design A1, which was a 40-foot doweled slab with an intermediate tied joint in the middle of the slab at 20 feet. Design A2 was the same as design A1, so the difference was they had area-wide reinforcement wire mesh. And design B was a 40-foot doweled slab with 2 intermediate tied joints at 13 feet and 4 inches. The main objective for this project was to evaluate the effect of joint configuration and joint spacing in pavement performance. Project 3 was located on US 50, about 45 minutes east of St. Louis. This was 7.5 miles of full-depth HMA. This project was divided in 15 different sections, and there were different combinations of subgrade line modification, the use of under drains. We had 3 different pavement thicknesses, 9.5, 11, and 12.5 inches, and we were using also 2 different types of asphalt binder, AC10 and AC20. The main objective of this project was to validate the mechanistic design proposed by the University of Illinois, and the design that the mechanistic design procedure came up with was an 11-inch HMA over lime-modified soil with under drains. Project 4 was located near Project 3. It consisted of 9.7 miles of cement concrete pavement. And the first 4 miles were 9 sections of CRC. The 9 sections were different combinations of sections with seal edge joints, under drains, and 3 different pavement thicknesses. Now, it's really important to mention that this CRC was not mechanistically designed, but we were interested in looking at the pavement performance with respect to thickness and all these other different constraints. The last 5.7 miles of this project were jointed concrete pavement. We had these 5.7 miles were divided in 18 different sections, and the sections were different combinations of seal edge joints, under drains, different pavement thicknesses, and we had 5 different drain configurations: the 20-foot, the 40-foot, and the 3-hinge joint designs that I introduced earlier. The main objective of this project was to validate the predicted deflection and strain values in PCC sections. So some of these sections were instrumented with strain gauges. All of these sections were open to traffic in summer of 1986. So after construction, we were very interested in the early age performance of these sections. So we collected some data from strain gauges, FWD, tipping buckets, and distress surveys. And we were able to draw some conclusions. So for the full depth HMA pavement, we verified that the structural performance improved with increased thickness. We noted that the only sections that showed any deterioration were the thin sections in Project 3, the 9.5-inch thick sections in Project 3. We also noticed that there were generally higher deflections in thinner sections. We also didn't see any clear correlation between asphalt viscosity and deterioration. Both the AC10 and sections built with AC10 and AC20 were performing equally. We also noticed that the sections with lime-modified soil yielded a higher modulus, and it was noted that during construction, sections with lime-modified soil provided a better construction platform. And we also noticed that the under drains did not show any tangible benefits. We used tip and buckets to evaluate the effectiveness of these under drains, and the results were pretty inconclusive. With the jointed sections, the strains in the slabs were really difficult to obtain. A lot of the sections were instrumented with strain gauges. We ran both static and dynamic tests. And the static tests were not very reliable due to a lot of factors affecting the data, such as baseline temperatures, curling stresses, and load transfer efficiency. Also, we run dynamic tests at different speeds with very negligible differences. And we had a lot of issues with data collection due to electronic noise interference with the strain gauges. And the only valid data that we were able to collect was in 1989, after we installed some noise filters. The measured strains values were way lower than our theoretical values, and even though these indicates that the proposed mechanistic models are conservative, there were a lot of factors affecting the readings, so we don't feel really comfortable using these as the sole decider of whether we were conservative or not. Therefore, for the objective 2, which was to validate the strains and deflections, was abandoned, and we wanted to analyze the performance of the sections based on thickness, the use of under drains, joint sealing, and joint configuration. So that being said, we noticed that the short panels performed better. By this time, all of the 40-foot panels showed some sort of transverse mid-panel cracking. We also noticed that the thinner sections exhibited more distresses. And also through coring, we saw that the sealed longitudinal joint sections had a drier subgrade. But now, even though the subgrade was drier in the sections with sealed joints, there was no clear difference in performance within the sections that had and didn't have sealed edge joints. And by this time, after 5 years of being open to traffic, the CRC sections showed very good performance, and there weren't any distresses recorded at that time. So we were very interested in continuing to see what was going to happen with these sections, so we continued keeping an eye on them, and we did it through multiple different things. We did condition rating surveys, CRS. This CRS is unique to Illinois, and is mainly used for programming. CRS looks at the immediate pavement condition, and this is collected using a video van. It gives the pavement a value between 1 and 9, and usually when CRS hits a value between 5.5 and 6, it triggers rehabilitation. Now, CRS has a couple of drawbacks. A lot of the sections are lumped based on the construction or rehabilitation contract, and it's not very detailed. So, due to that, we decided to do some manual distress surveys. Manual distress surveys was collected when we had available manpower, and they're a full-length surveys. They give us a detailed distress mapping along the whole section, and they are collected using the internal pavement distress manual that was developed by us based on FHWA distress identification manual. So Project 1 performed according to our rehabilitation models. Now, IDOT rehabilitation models were developed for pavement selection and life cycle cost analysis calculations, and what this says for HMA pavements is that they are supposed to receive their first overlay at year 15. Now we see that the values on CRS hit in between 5 and 6 at around year 15. Now this section was overlaid at year 21 in 2007, and the overlay was triggered mainly by environmentally induced distresses such as block cracking and raveling. We also noticed that Section A, the one was built with AC10, outperformed Section B, the one built with AC20 after the overlay. And we assumed that the difference in performance between both Sections A and B had to do that cracks in softer mix are less likely to reflect the overlay. And this helps us validate our policies in binder selection based on temperature across the state. Project 2, we see that the CRS values show no difference in performance among all 9 sections, and this really highlights the shortfalls of CRS. We see that it's not very detailed, and it lacks to present the real picture of what was going on in the field. So thankfully we did some manual surveys, and we noticed that the 15-foot section showed very few low severity distresses, and mainly they were localized distresses and spalling. The 20-foot section showed very few and some medium severity distresses, and there were also spalls and localized distresses. But all of the 40-foot slabs showed transverse cracking, and mostly of medium severity and some high severity cracking. And some of the high severity crack had some serious faulting. We also noticed that the hinge joining section showed very few low severity distresses. For Project 3, we decided to lump Project 3 based on the thickness. So the 9.5-inch sections showed some rutting and stripping within 5 years of construction. Now it's important to know that the US-20 and US-50 mixes used for this project did not contain anti-strip. Now these sections provided us very important insight for the development of TSR testing procedures and the use of anti-strip that came in the late 1980s. We also noticed that the sections without line modification and underdrains required extensive patching. And we see that section M and MI did not have line modification, and their CRS is significantly lower than the rest of the 9.5-inch sections. And most of these 9.5-inch sections were overlaid with 2 1/4 to 3 inches of HMA in 1994. So a very early overlay that we believe it was triggered because of the in sections and the lack of anti-strip. Now, 2 of the sections were overlaid in 2007, so they vastly outperformed the other 9.5-inch sections. Now, these sections were a little bit different. Section N was a very short section, and it had one structure within it. So we believe that the very short section might not be a good representation of the 9.5-inch section. And section O was a transition section between the 9.5 and the 11-inch section. Now the 11-inch section, we only had section P. This section performed according to our rehabilitation models, once again hitting the 5.5 to 6 CRS values at around 15 years. And this was overlaid in 2007 due to some fatigue cracking and then some environmental deterioration, such as raveling. We had some centerline deterioration as well. The 12.5-inch sections were overlaid in 2012 due to just mainly environmental distresses. And we also noticed that we have seen that the environmental causes drive our rehabilitation, and our pavement selection models reflect this, that we're mainly going to have environmental causes. This shows a picture of all the CRS values of Project 3 lumped together. Now for Project 4, we decided to organize them by joint configuration. So for the 40-foot panels, all panels had showed mid-panel cracks, regardless of the existence of under drains and fill joints. And these mid-panel crack led to a discontinuity without load transfer, and most of the cracks ended up faulting and vastly affecting ride quality. Now, some of these sections were overlaid in 2007, and a lot of the sections that were overlaid showed reflected cracks, and most of the reflected cracks that we observed in 2010 were at the very least of medium severity. The 20-foot joint sections, they showed few low severity cracks. Some of these were also overlaid in 2007. The sections that when we surveyed it in 2010, we couldn't find any reflected distresses in the overlaid sections. And some of the sections had minor faulting, but this was an issue with emergency vehicles going into the area. Therefore, some of the sections had to be overlaid earlier than we expected due to this issue with emergency vehicles. Now, also, some of the 20-foot jointed sections were overlaid because they were adjacent to a 40-foot joint section that required an overlay, and for the sake of programming, it just made sense to overlay them. Now, the hinge jointed sections showed very good distress, very good performance. They had very few distresses, and they were built until 2011. Now, even though this project and the sections on the US-20, the hinge jointed sections in US-20 performed satisfactorily, the hinge jointed pavements are not practical in urban settings due to the vast amount of discontinuities, such as curbs, meeting no things, and utility cuts. And these discontinuities tend to induce a distress. Now, Project 4, the CRC sections are still buried to date, and the only rehabilitation to date is some isolated patches. Here's a snapshot of all of the sections, one table. So this brings us to some conclusions. We saw that the asphalt binder selection according to climate is crucial for performance. In the original mechanistic design, we used AC20. Now IDOT assumes a PG64-22 for design, and we require a PG-modified binder and surface lift for every pavement. And we also looked at the influence of temperature and location of the state for binder selection for pavement design. We also saw the joint spacing and configuration is the main reason for slab failure. When we placed the short slab, next to the 40-foot slabs, it was evident that the 15-foot slabs were performing much better. We now require 15-foot dowel joints over 4 inches of stabilized subbase. And even though the hinge-jointed sections performed well in this study, we found that the hinge-jointed sections did not perform well in urban settings, as I mentioned earlier. We also concluded that pavement thickness and subgrade selection influence pavement deterioration. We now require 12 inches of modified soil or granular material as a subgrade for all pavements. And this is due to the assumption that the original grade has a CBR of 3, and we need to have 12 inches of cover material to prevent rotting and provide a good construction platform. And surface drainage is included as a matter of practice. We saw how in this specific project the under drains didn't show any tangible benefits, but through other studies we have concluded that that preventing the subgrade from saturating is good practice. So we continue looking at these sections to date, and we believe that pavement design is an ever-changing process, and these sections will continue to give us very important information. So I hope I didn't bore you guys to death. I'll take any questions if you guys have any.
I am now unmuting the audience in case anybody has any questions. Okay. Looks like no one has any questions. Thanks, Juan.
Thank you, Annie.
Now we will start our second presentation. It's going to be Mark Grinter and Mr. Zhou from SIUE. And they will start shortly.
Hello?
Hello.
Yeah, can you hear me?
Yes, it's a bit quiet. It's a bit low, so if you could just be a bit closer to the microphone, that would help us hear better.
All right, how about now?
That's perfect.
All right. Can you see the PPT?
Yes, we can see your presentation.
All right, yeah, my name is Huaguo Zhou from SIUE, and I'm going to present this project with the Mark Grinter. So let me see if I can move down. First time to do this. Okay. All right. So first I'd like to go through all the project tasks that we complete for this project. And as you can see, we separate the project as a two phase, phase 1 and phase 2. From the January 2012 to the June 2012, that's phase 1. We complete the 4 tasks from data needs all the way to the preliminary documentation. And the second phase is for the second year, from July 2012 to by the end of the June. So now we are working on the final report, and so by the end of this month, we will have a final report for the editing. So the main objective for this project is to determine the cost-effective method to collect highway inventory data not currently stored in the IDOT database for implementing highway safety manual. That's the main purpose. So we also like to see the data can be used by other office, in the IDOT and the local agency. So for the data needs part, we collect existing highway inventory database by the IDOT, include the IDOT GIS database. and also IDOT pavement inventory database, and also NAVTAG database. And we studied all these three databases and see what kind of the highway inventory data is already there. And then we looked at all the input data for the highway safety manual, all the modules for the rural two-lane highway and the rural multi-lane highway and the urban, suburban, arterial, and the interstate freeway. And we looked at all these modules, see what are the inputs. So we try to identify what kind of data we need to collect. So based on the study results, those are the main data we need to be collected. So roadside slope and a lot of information about roadside fixed object and the density. So and also offsets to the roadside fixed object. Some like median barrier and how long it is. This is more like linear objects. Okay. And the median barrier width and the clearance zone, also some super elevation, the curve information need to be collected. So some information already in the IDOT GIS database. So some information we have to collect in the field, and the roadside fixed object are the main information that we need to collect in the field, and also roadside slope. So we did a comprehensive literature review, and we studied, and those are the method has been used by other state agency for the highway inventory data collection, include the field inventory, GPS, GIS mapping, photo, video log, satellite imagery, and also laser scanner, remote sensing, mobile LIDAR, and airborne LIDAR. So we study all these methods and how they be used by other agency and what kind of information they can collect. So based on this table, as you can see, the photo video log can only probably collect part of the roadside objects, not include the offset of the information. And also for the satellite imagery cannot collect the vertical object. It's not visible for that. So those are the literature review results. In addition, we also conduct a national survey. We send a survey questionnaire to 49 state agencies and also 7 province in Canada. So we try to get feedback from the state agency what kind of the highway inventory method technology they used. So based on the survey results, 60% of people respond they use the GPS GIS, and 57% they use the field inventory, and the area image, video log, photo log that comes the next. So we only find 2 or 3 agencies they start to use the mobile LIDAR. That's a new technology. So, and also we ask each agency to evaluate the method they used, include the equipment cost, data accuracy, and the data completeness, and also the overall data reduction time, data reduction cost, and the data storage requirement, and overall performance. So as you can see from this figure, you will see their feedback for each different method. So I'm going to turn it over to Mark, and he's going to talk about the field experiment.
Good afternoon. So we, on the basis of our literature search and the survey, we identified different types of technologies to explore, and we conducted actual field trials of those on the GPS data logger, a robotic total station system, a video log system, deriving data from available satellite or aerial imagery, and using a mobile LIDAR system. And for our field trials, we identified 4 different types of road sections to evaluate the systems on. One was a multi-lane rural highway here on campus. It's a 4-lane divided highway, low-speed traffic. Another was a section of rural 2-lane highway, Illinois Route 140 in northern Madison County, Illinois. The third section was a section of Interstate 270 in the vicinity of Collinsville, Illinois, and the fourth site was a urban suburban arterial street known as Governor's Parkway, just to the east of Edwardsville. And all those 4 sections we applied all these systems. So the GPS data logger and the robotic total station, we tested those simultaneously with 2 different crews along 1.3 miles of highway alignment. And we were able to collect all of the parameters that are required for the highway safety model with that system. The video log system we used over those 4 segments and some additional alignment, collecting a total of 28 miles of video data, and we were able to extract everything except the roadside slope and the horizontal offset to roadside objects. For satellite imagery, we used existing imagery and analyzed 7 miles of alignment over those segments that we discussed earlier. And we determined that we couldn't extract all of the highway safety manual related features that we would have needed to complete the manual. Then finally, we leased a mobile LIDAR system and ran that system over 14 plus miles of road segment, and then took that data and reduced that data, and we were able to retrieve all of the parameters required for the highway safety manual method using that system. For the data reduction for those various systems, for the GPS data logger and the robotic total station, we used AutoCAD. That's what we have here in the university, but we could have just as easily used MicroStation or any other of a variety of civil engineering surveying packages, because that just generates both of those systems just generate XYZ coordinates that can be imported into virtually any CAD system. The photo video logging, we used a GIS package and then a manual review of the video to create the data extraction. For the satellite imagery, they use Google Earth Pro data reduction, and for the mobile LIDAR, we used a point cloud post-processing software that was proprietary to that manufacturer of the LIDAR system that we used. So we needed to analyze the results of that. I'm going to turn this back to Hugo here in a minute to compare these different systems.
Okay. When we try to evaluate the different methodology, we decided to use the same kind of criteria to do the evaluation. So because when we do the data collection, different method, we collect the data for different lengths. For example, the photo video log, we collect 28 mile. But some other method, like a GPS data logger, you require a lot of the field data collection time. So we did 1.3 mile for that. Mobile LIDAR, we did 14.2 mile. Because the lengths different for different methods, and the data collection time in the field are also different. So we all calculate based on the number of man-hour per mile for each method. So that can help us to compare different methodology. Based on the results, we found out the photo video log total time probably 1 man-hour per mile. That's the time required for the collect all the data we need. So satellite imagery is 1.5 mile, and the mobile LIDAR is 5.5 mile, and the GPS data logger and the robotic total station are the 2 highest one, the 7 hours per mile and the 12.5 miles per hour. per mile. So the next, we also try to use the multiple criteria metrics to rank different perspective or different area for the different method. As you see, we list two separate large category. One is the field data collection, another one is the data reduction part. So for the field data collection, we have to consider equipment cost, labor cost, collection time, and the safety, and also the data completeness and the accuracy, also disruption to the traffic. For the field data reduction time, we need to consider the software cost and some label cost, data reduction time, and the data storage size. So we use the scale 1 to 5. The 1 is poor and the 5 is excellent. Oh, 1 is the best. Okay, 1 is the best. 5 is the worst scenario case. So we try to rank each method based on this scale, and we add all these together, and the method with the lowest number score that probably comes out the higher ranking. And also we like to because the different agency may give different weight for each of these items, so we like to collect input from agency for the weight for each of these criteria. So then we can estimate a weighted total score for each method to give a final ranking for the data collection technology. We also did the cost analysis for each different method. We used the $30 per hour for the regular training person, but for some like mobile LIDAR data reduction, you need some special training person. So we use $50 per hour as a unit to estimate the cost per mile for different methods for the data collection. So we get based on the man hour used per mile, we times the unit cost. We estimate the cost for each different method. So the mobile LiDAR come out is $422 per mile. So with that, that's all my part. I'm going to turn over back to Mark.
So for our actual tests, these are the systems again that we reviewed, and the individual results of each system are that the GPS data logger we found has the capability of collecting all of the different categories of data used by the Highway Safety Manual, and that it meets the accuracy requirements of the model. A shortcoming is that GPS outage along areas of tall buildings or significant tree cover is a definite problem. We encountered that several times along tree line segments of the rural highways, that we would lose data lock and not be able to collect features. So the way the current technology works is you have to hold the device next to the feature. The other big limiting factor is that the crew member has to actually go to the object to collect it. So if you're collecting edge of pavement or edge of shoulder or center line, that means the crew member has to physically be standing there, and setting up the traffic control for that is time consuming, and even then your crew is still at risk. What we found is that GPS outage and crew exposure shortcomings are now, we are able to overcome them with the next generation of equipment that's just come on the market. And that equipment integrates a rangefinder, compass, and inclinometer so that you can remotely collect information. And this is an example of that equipment, and it's nearly the same price point as the old system where you had to actually be at the point. So I think if anybody there is in the is in the market for doing data collection using GPS for GIS applications, that this machine and or an equivalent integrating the same technology is going to rapidly overtake the market and overcome those limitations of GPS outage and crew exposure. Because the range on these things is up to 1,000 meters from where you're standing, and you're still generating sufficient accuracy information on the data. We also tested a robotic total station using a state-of-the-art Trimble robotic total station. We found that we can collect all the data we needed. It exceeds the accuracy requirements of the highway safety model requirements. It does have some additional initial setup time that the data logger doesn't have, and due to the fact that the robot stays in the same place, you have line of sight problems with the machine due to both vehicles and to intermediate landscape problems. And also the crew member, like with the handheld data collector, has to actually walk to the point or walk to the object that you're collecting data on, so you've got continued exposure of crews with this method. The photo video system, we set up a video camera linked to a GPS system in a vehicle, and we were able to drive at 40 plus miles an hour. So it's the field data collection time per mile is very low. We could do most of the feature extraction that we needed, except for the roadside slope and some of the offsets to the fixed data. So this system is very efficient for collecting data. It's a good use of the data reduction time is relatively efficient, but it does have this inability to collect a couple of the parameters that are in the safety manual. Satellite aerial imagery, we used existing imagery that was available over the targeted segments that we studied. We found that the data extraction is similar to the video extraction as compared to objects per minute, but there are multiple categories of features that you're not able to get at with this system, roadside slope being one of them, and any small vertical objects that you would see in a horizontal view aren't visible enough in the satellite aerial imagery to be of use. The mobile LIDAR system that we demonstrated, we could collect all of the data on all of the categories. The data collection cost is higher because we're looking at approximately $600,000 worth of equipment that we have in the field to do this time, but we're able to do that at highway speeds without exposing the crews to traffic. But we find that when we took that data back to the office and wanted to extract meaningful information at it, we were looking at 5.5 hours of data reduction time per mile of data collected. And if you were going to do large quantities of roadways, you'd have to store large, and I mean large, quantities of data in order to be able to handle the material generated by the system. But again, you're collecting it without exposing your crews to traffic or the need to close the roads. One thing to think about is that there are multiple folks doing LIDAR data collection in Illinois. And this is a map of the current data collection LIDAR that is involved with the U.S. Geological Survey and the Illinois State Geological Survey. You can see that over half the state has already been mapped with some form of LIDAR. This material is accessible online with appropriate login procedures from Illinois Geological Survey, and it's likely that outfits like Google Earth and Bing and those folks are driving virtually all of the country now with systems, and the LIDAR data generated by those may in the near future be available to us, so there wouldn't be a need to have the acquisition cost. We just need to figure out how to use the existing data. So our recommendations, which Hugo and I are going to, I'll let Hugo chime in on in a minute, is that the field inventory collects all the data we need at the accuracy we need, but it's very cost intensive and time intensive, so it's only suitable for special projects that have over a short period of the road where, for instance, say we had a new build situation or a change of conditions and we just want to go out and investigate that initial spot. Otherwise, this is not the approach that anybody should consider for a statewide method of collecting highway safety data. The photo video log, if you ask me today, for the lowest dollar possible, generate from new information a highway safety manual features for the entire state, and we can live without having to know the side slope data. This would be the methodology of choice. But the apparent emerging technology that is the way to handle this, I think, is with the mobile LIDAR and to rely on data collection that's used by other agencies and provided already free, and augment that and then come up with efficient ways to extract the data and obtain the highway safety model features that we want to record with that method. So do you have any other? Okay, so if there's any questions, we can both hear on this end, and either one of us will be happy to answer them.
Okay, I'm now unmuting the audience in case anybody has any questions. You can go ahead and talk into the phone. So you can go ahead now with any questions.
This is Priscilla. Tobias, I guess I don't have a question. It's more of maybe a comment, is that with MAP 21, there in the HSIP program, there is language in there about improved data systems, data collection, and FHWA has provided some guidance on data elements that should be collected, and they will be doing rulemaking on data elements that will be shall be collected. And it's entirely possible what is a should will become a shall. And so, and I was actually just recently asked if I would serve as a task group chair for at the national level in this one association dealing with data, geospatial mapping, and strategic highway safety plans. So I think this project is very timely, and we will need to be looking at all those federal requirements that are coming down, even kind of bigger than the highway safety manual.
Okay, thank you, Priscilla. Anybody else have any questions or comments to make?
So Priscilla, can you provide us separate from now the specific information on the literature where you're seeing this discussion about should and shall?
Yes, yes. I mean, the rulemaking hasn't come out yet, but I can provide you the guidance that we're getting right now that came from MAP 21. And essentially, I mean, they're saying, okay, you have these Meyer elements, and they'll be based on ADT, the breakdown. And, I mean, I know ramps and curve data will be definitely in there. But the rulemaking, I don't know if I got a schedule for that. But yes, I can provide at least the guidance that I have right now, and then as soon as I know something with the rulemaking, then I can share that also.
Okay, great. Because that's really critical to selecting the technology. If you know it has to do these things, then it has to do them, and you can rule out obviously things that aren't systems that aren't capable of doing that. But
yes, and I agree. And whatever can be done the most efficiently too.
Right. Any other questions? I've got a question maybe. Does anybody there in the audience use handheld GPS data loggers? Are you currently using any for any of your field crews?
On the background, and it's wrapping up.
One other thing I might add is that, Ms. Priscilla, there's also some additional equipment that he used, let's say, like to get pavement marking that can, depend where it will, you can drive through the job and basically it'll use the LIDAR to locate your pavement marking and your pavement, I'll say, when I say quality, like where it's in places and where it's normal, and it can collect that data, and then when you go out to strike, then you just this piece of equipment to your truck, and it basically puts the pavement marking right back where it is. So I got some additional information of some different companies and things that are out there that I can provide to you and to Rob.
That is great.
You're guaranteed that I brought you a type of comments. Thank you. These actually might work for me.
Background noise is bad.
They're skinny ones.
Don't forget, everybody, that we can hear you in the background.
You have something to hear about?
If anybody has any more questions now, otherwise,
No,
thank
not
you
yet.
everyone for attending
Yeah.
this meeting.
Did she just send? Did she send?
And I've been on that, so I can't.
Okay, thank you, Annie.
They won't let me.
Thank you, everybody.
Thank
Bye.
you. Bye-bye.
Thank you, Annie. Bye-bye.
Bye.